Today we're going to do a lesson on stoichiometry and mole ratios. This is a very interesting part of chemistry. It's also a very commonly used area of chemistry in any kind of industry or any area where they are in the business of creating products. And before we get into the examples that show how we calculate or do some stoichiometry problems or use mole ratios, it is really important that you have completed this first section of our summary note. So in our content area, the main resource note is listed there. We're going to go to that in just a second. But it is very, very important that you have worked through these questions and the simulations that are there, the little activities for you to do, that you've tried these practice problems. Okay, so this chart right here, there's a chart set up for this balanced chemical reaction. Again, you'll know how to solve for that if you do the upper part of the summary note. Here's a second reaction to try. And then right here, I'm going to do these two examples, these stoichiometry problems with you. But if you have not done this upper part, you're going to be confused as to what I am doing. So it's important that you go through this summary note and that you complete all of the sections that I ask. So again, where you're going to find this is in content. We're in Unit 3. We're working our way down. We're in Lesson 9. And in Lesson 9, as usual, there is a what do I do? So here's the summary note for you to click on and make a copy of. And then you're going to click on the main resource note here, which is called Applications in Stoichiometry. And I want you to read through everything that's here. Okay, there's really good information. Some of it's interesting too about airbags, as you see. And I'll just wait for my Chromebook to, unfreeze. And then as we move through the summary note, there are some simulations here that we want you to carry out. Okay, so you're going to click on the start button and it's going to open up in a new screen. Here are your instructions, okay, to take you through these simulations. So, the whole thing, it's not going to take you very long to go through these simulations, but they're really good for you to get a handle on what is this concept of stoichiometry and how are we using this in chemistry. And for all of these stoichiometry problems or all of these simulations that you're doing, you need to have a balanced chemical reaction and you need to know what the coefficients are in front of all of your substances. And that's what, again, the summary note here, the resource note is taking you through all that, and they're getting you to see the relationships. So as we scroll down, there are some questions for you to ask. And then we eventually get down here to these stoichiometry calculations. And I'm going to do these two examples with you right now. So the first thing that we need to know is how do we set up a mole ratio? So sometimes it's easy for us to predict the amount of substances we're going to need or make in a stoichiometry problem. And many of the tasks that you did in the resource note, whether you're making cars or you're making sandwiches, they had very easy numbers to work with. But sometimes the numbers aren't that straightforward and you can't do the math in your head. So the first thing that you need to have is a balanced chemical reaction. And if you don't have that, you cannot do stoichiometry and you cannot set up a mole ratio. It's impossible, okay? Because we now know that the coefficients in our balanced reaction represent mole values. So it's very important that we have those present. When you set up a mole ratio, you're always going to have an unknown substance and you're going to have a known substance, okay? And what this means is the unknown substance is what they are asking you to solve for. So they're going to ask, how many moles of a reactant do you need? How many moles of a product are you going to make? And they're going to compare that to a known substance where you are given actual data for that known substance. So you're basing your calculations off of it. So when we set up a mole ratio, we have to take this unknown and known substance and set it up in a way that will allow us to calculate what we need. So we always figure out the moles of the unknown substance, and we compare that to the moles of the known substance. And then we equate that on the other side of our ratio in a similar way. So we would have moles of our unknown in the numerator, and we compare that to the moles of our known in the denominator. Now, when you look at that, you say, okay, it's the same thing. Why are we setting up the same thing on both sides of that equal sign? It is the same in terms of you're using the known and the unknown value. You're also using mole values, but the mole values that you use are different. So on the right side here, your moles come from the coefficients. Okay, so remember that in the resource note, we have learned that those coefficients in the reaction, okay, so for a balanced chemical reaction, are fixed mole values. So on the right side here, those mole values come from the coefficients in the reaction. Okay, there's my short form for the reaction. If we move to the left, these values here are our actual mole values from the questions. Okay, so this is going to be like actual data that they give us, and they are either asking us to solve for, again, a reactant or a product, and we get those values on the left side over here out of the question itself. Okay, right side over here from the coefficients. Let's try one. So it says, given the production of magnesium oxide from its elements, how many moles of magnesium are required to produce 4 moles of magnesium oxide? So if I look at the balanced equation right here, what I can see is that if I had 2 moles of magnesium, I would need 1 mole of oxygen, because remember, if there's not a number there, that implies there's a 1. And I would make 2 moles of magnesium oxide. Okay, so this is in a perfect world. If I started with 2 moles of magnesium, and I mean, in the simplest sense, you could start with 2 molecules of magnesium. You would need 1 molecule of oxygen. You'd make 2 molecules of magnesium oxide. But what we know is that molecules are really, really, really small. And if we were carrying out a reaction like this in a factory, 2 molecules is not going to do anything. So you need to scale that up to a mole, right? And a mole just represents a large amount of molecules or atoms. So we would need 2 moles of magnesium to react with 1 mole of oxygen and make 2 moles of magnesium oxide. Well, one of the things that I like to do is I like to write underneath my substances what I know and what I don't know. So it's saying how many moles of magnesium. So this is my unknown. Okay, I'm going to try to figure out, well, how many moles of that do I need? Because they're not going to make 2 moles of magnesium oxide. They want to make 4 moles of magnesium oxide. So over here, we write down that we're going to make 4 moles of magnesium oxide. And this is kind of a simple mole ratio for us to figure it out. We can see that the coefficients are exactly the same on both sides. So if I wanted to make 2 moles of magnesium oxide, I got to start with 2 moles of magnesium. I want to make 4 moles of magnesium oxide. What do you think we need to start with in terms of magnesium? So this is a simple ratio. You can probably do it in your head, but I'm going to set it up for you using the ratio that I showed you on the previous screen. So my unknown is magnesium. So I want to figure out how many moles of magnesium if I am using 4 moles, this is my known, of magnesium oxide. And then I equate that to the coefficients for each of those. So I will have 2 moles of magnesium, because that's my unknown. and I will make 2 moles of magnesium oxide. That's my known. So what you notice is that the magnesiums, and I'm just going to change colors here to make it simpler. On the numerator, I have my unknown is magnesium. I have my coefficient for magnesium on the other side of the ratio. My known value is 4 moles of magnesium oxide. I have the coefficient for magnesium oxide on the other side. Okay, so remember, it's coefficients over here, and here is actual values from the question itself. Now, this is an easy one. Okay, what are we going to do? Well, you take your denominator and you cross multiply it by 4. Okay, so to get my moles of magnesium, I am taking 4 moles of magnesium oxide. That's from the denominator that I am cross multiplying over. I multiply by 2 moles of magnesium, and then I divide out by 2 moles of magnesium oxide. And what we see happening is that my moles of magnesium oxide cancel because they're over top of each other. They're divided out. Those 2's actually cancel out. So I end up with an actual value of 4 moles of magnesium. Okay. So remember that the coefficients in your reaction are, fixed values. They represent the proportions that your substances have to be in order for the reaction to be carried out. But the odds that we start with 2 moles of magnesium from the coefficient over here, or 1 mole of oxygen, it's very rare that we would have those exact values. But still, the proportions exist, and we can scale up or scale down the other quantities. Let's do this one here. So here's the reaction for water decomposing into hydrogen gas and oxygen gas. And it says how many moles of oxygen. So we're going to stop right there and we're going to come over to oxygen and fill that in. We do not know the moles of oxygen will be produced from 6.2 moles of water. So we come over to water and we write down 6.2 moles right there. Okay, so remember, these are the actual values. Okay, and they don't mention hydrogen here, and that's perfectly fine. You can only put 2 substances in a mole ratio, so they just have to pick 2. They can't have 3 in there. And we notice the fixed coefficients. So if I had 2 moles of water right here, I would make 1 mole of oxygen. Well, I don't have 2 moles, I have 6.2. So how many oxygen molecules will I make? Well, it's still a 2-to-1 ratio. Okay, it's still a 2-to-1 ratio, but we're going to set up our little mole ratio that I taught you to help you out with that. So my unknown is oxygen. So I'm going to say, well, I don't know what the actual mole value of oxygen is. I do know I'm starting with 6.2 moles of water. Okay, that's my known. And remember, on the other side, we put the coefficients for those substances, and they have to match. So if my unknown is oxygen, then I need the mole coefficient for oxygen on the other side. There's no number there, so we know it means a 1. And my known value is water, so I put the mole coefficient for water in the denominator. We're going to cross multiply our water up and over. So 6.2 times 1, we're going to divide it by 2. And we're going to just set this up for you so that you can see us moving the numbers around. So 6.2 moles of H2O. I'm cross multiplying by 1 mole of oxygen. And then divide everything by the denominator, which is 2 moles of H2O. My moles of H2O will cancel out, and I'm going to take 6.2 and divide that by 2, and I get 3.1 moles of oxygen. So there are a couple of examples for you to see as to how we actually set up a mole ratio. Sometimes you don't need to set up the ratio. You can just do it in your head, which is fine too. But sometimes if it's more complex numbers, we need to set it up so that we don't make any errors.